Good afternoon, everyone. Thanks to those who stayed. Having now this last part of type-safe embedded domain-specific languages. And to start, I'd like to first ask if anyone has any questions about anything that was said yesterday, about anything that they've found out, discovered, looked after. Okay. So today we're going to talk first about type-safe embedding. And what that means exactly is that if before we were talking about DSLs as this broad thing that they can be internal DSLs or external DSLs too, now we're going to focus only on the internal ones and those that are embedded in a language that has a type system and a sort of powerful type system such as Haskell has. And first of all, I'd just like to remember some things that we discussed in the past session, like that a DSL is basically a model, a domain model, a business model that you have, and you develop a language that's comprised of syntax and semantics to solve some problems in that domain. And we basically define syntax as data that we can manipulate, whether that be an abstract syntax tree that we can optimize, peek into, or whether that be the semantic domain to which we're trying to interpret our values. For example, in order to develop a language that operates, that produces finally some side effects in the IO monad, we have the choice of first defining our syntax as an abstract syntax tree, which we can then interpret into the IO monad, or we can just define our syntax as some function to the IO monad, which it can then trivially interpret into the IO monad. And another view of DSLs is having a domain, a model, and plus primitives, composition, and interpretation, where primitives and combinators are basically the syntax of the language. So what exactly we want to embed languages is in order to be able to feast on the host language, to take the good parts of the host language and not have to implement everything in LDSL, for example, control flow, basic arithmetic expressions, type system, and for effects, data types. And unfortunately, we also get recursion in the case of Haskell, for example, so we cannot always escape the Turing complete setting. That's mostly only possible with external DSLs. But we also would like to, for example, integrate a DSL and the way we use a DSL with the types we have in Haskell for the other parts of our application. When we're, for example, in a language-oriented programming setting, if we have already a system, but we want to use a DSL inside that system in order to build some parts of that system, we'd like to be able to make use of some types we already have for our application inside that DSL, or build some types inside our DSL too. So there are two basic techniques for embedding languages inside other languages, and that's shallow and deep embedding. We have already seen those sort of in the previous session, but we've never discussed them thoroughly. So first of all, the difference between both is who exactly does the job of lifting stuff inside our DSL. Is that the syntax or the semantics, are the interpreters or the constructors, the combinators, the primitives? And there goes also a difference in extending our DSL. What exactly do we need to extend to add to in order to extend our language? Do we need to add new interpretations or new constructors? And we're going to see that dip is simple, but shallow is direct, because this is an example of a shallow embedding. We have already seen this in the past session. This is the data type definition for the phone builder DSL we use at Lumi. And we can see it takes a function. It's a function basically that takes a parameterized argument of props, a value which is the thing that we actually added in the form. And it produces finally this tuple, this anonymous record of a UI and a valid result, maybe. Another, this is called a shallow embedding because we're basically just, instead of building an abstract syntax tree that we can then inspect as data and manipulate, we're just using basic Haskell values, basic values of the host language in order to embed our own language. Hopefully some of you can see that it's trivial to interpret this DSL. It's also a little bit hard to add new interpreters, because what if, for example, we wanted to, I don't know, interpret it into the, I have no idea, but what if we wanted to interpret it into documentation? like we don't have anything here in this value that can give us some documentation, right? So we'd need to add something that gives us some static documentation to this data type definition, and then we'll have to rework all the constructors, all the combinators of this DSL. So yeah, a syntax is defined in terms of the semantic domain, I've said that. And adding a new interpreter might, yes, imply adding some new set of constructors too, because like you might also want to just restrict some part of the DSL to just a single interpretation. You can also refactor the whole semantic domain and rework all the constructors. There's a nice paper that discusses like how you can make shallow embedding more extensible. I've linked to it, and not linked, but I've added the reference by the end of the talk. It's called Folding Domain-Specific Languages, and it discusses how we can make shallow embedding a little bit better. And another way of representing the same DSL could be with deep embedding. And that means basically like building this abstract syntax tree, which you can then manipulate. How many of you here are familiar with GADTs? Okay, so for those who are not, like this is basically the same thing as defining like data, form builder, props, value, result, equals, and then we define each of these cases. Like text box is something that takes no arguments, right? So it just returns, as all constructors are functions, we can interpret these as functions too, like we use the function syntax here. So text box and passwords are form builders that take no arguments. But the cool thing about GADTs is that we can treat some type arguments as indexes. And that means that like they sort of depend on the values that on these constructors, right? They sort of depend on the values of this type, right? Because a text box is not just a form builder props value result. It's a form builder props value result where value is a string and where result is a string, right? So we sort of carry these proofs around that these arguments, these type arguments match these values, right? So yeah, for those of you who have seen and experimented with this DSL in the past session, we can, for example, identify the focus combinator here that is now defined as a member of this abstract syntax tree, because before we could define it as a combinator that just takes the stuff we already had and just manipulated it in some way, but now we just have this abstract syntax tree, so we have to find a way of making focus something that we can treat abstractly as well. And I hope that some of you can see that it's quite trivial to add new interpretations to this language defined in this way with deep embedding, because we can just like define a function that takes a form builder like this and turns it into anything else, because the syntax tree is abstract, so we can interpret it into anything. Yeah, I've said all this, and yeah, one important like bad part about deep embedding is that adding new constructors might imply reworking all the interpreters we have, right? So people usually recommend shallow embedding more for like a business setting where you're doing software engineering, because it's not often the case that we have to write new interpreters for a DSL. We often need to add new constructors, new syntax elements to our language.
Why is reworking? Isn't just like adding
Yeah, exactly. It's basically just adding another case.
You don't have to usually, I guess, rework, like rewrite everything.
Yeah, you don't have to rewrite. That's like exactly. Rework just basically means that you have to refactor it in some way, right? Does anybody have any questions? Nope. Just please stop me to ask at any moment if you feel like it, okay? And yeah, as we see like this duality between deep embedding, shallow embedding, also the duality between the problems that they bring, it's perfectly summarized by the expression problem, which was stated by Simon Peyton-Jones. And it says that the goal of defining the expression problem is basically that we have to define a data type by cases, in Haskell at least, right? Where one can add new cases to the data type and new functions over the data type without recompiling existing code and while retaining static type safety. So like, we want to add new cases to either the interpreters or to the syntax of the language, right? We want to either add new interpreters or new elements to the syntax. So how exactly do we do that without having to recompile or retouch or refactor things that already exist? So I think I'm going to go over this. I was not planning, but yeah. There are a few ways we can also take advantage of some constructions we already encounter in day-to-day in Haskell. I'm going to talk about monoids, applicatives, and monads shortly, just so you can see what exactly you can do with those and what you cannot do with those. So DSL based on monoids, you basically can just manipulate data and accumulate data, right? You just have a bunch of data that you can accumulate. And for those who are not familiar with a monoid type class, it's basically defined as 2 split type classes now in Haskell in the base package. The first one is the semi-group class, where you just take 2 elements of a type, and you get another element of that same type, right? It's basic rule is just associativity, I guess. I'm not sure if there are any more, just when you introduce monoid, right? And the monoid type class, you just add an identity element that is, this empty is the identity element of the I don't know how to call that operation, the append operation, append, yeah. And an example of a very simple, I'd say, monoidal DSL is the one for building documents. It's kind of like, it's not trivial, I'd say, but it gets kind of obvious when you finally grasp it, that this DSL, it cannot, for example, produce, manipulate any values outside of those that are defined here. It's not like the form builder DSL we played with yesterday, that you could like produce values out of thin air, you know, and use the values that were produced, that were taken out of the UI, and build other structures with those. Like you can't produce any sort of side effects or context with these. So for example, like this, we have a document that can be defined as a series of blocks or inline elements, and we just learn how to group those together, right? It's a very simple DSL, but it could be a very effective one for describing basic documents. I'm just going to go over very quickly over these because they're like, it's better to see these things in practice, I think, and we're going to have some live coding session after this. So this could be the basic definition of a document using that DSL, right? We're just folding this array of things, which basically just means that we're appending the first block here with the second block, right? Because that's what fold does. If you give it a foldable element, it just like appends everything inside a monoid, and document is a monoid. So, and this is equivalent to this if we use a nice, debatably nice extension of Haskell called rebindable syntax. Some people abuse it. I don't have any strong opinions on those, but we could just like say that the operator for sequencing monadic actions is now the append operator. So we can just write it like this, right? We don't need to fold it to treat it as an array. I should have added actually a more complex example so we could see like that it looks pretty nice, but I don't know, it could be confusing sometimes. Anyway, after that we have applicative functors, and these are like extended functors. We extend functors with 2 other operations where we can like sequence effectful or contextful operations, and the other one we can just like embed a pure value inside a contextful context, an effectful context. The type class is defined like this. I'm not going to talk about the laws because like we're just interested in the practical aspects of these, but it's interesting if you'd like to take a peek at the laws later after this. Like the applicative type class is defined in Haskell like this. You can basically like, given a functor f, you can embed a value inside this context, and ideally this pure thing here is the identity for this operation. So like ideally this context is pure in some sense, right? For some definition of what pure is, of what like this specific operation treats as pure. And this is called the apply operator, and it just basically takes a context that contains a function from A to B, and a context with an A, and gives you back a context with a B. This is isomorphic to this operation here, right? Because where you just have a context producing an A and a context producing a B, and you have a context producing a tuple of AB. So what is most important about this is that given only these signatures, we cannot build anything that has sequential dependencies, right? We cannot produce an effect conditionally based on a previous value, because it's more obvious to me when I look at this type signature specifically, because the effects are encoded in this f, right? The context is encoded here in this f functor. So if we're given an fa and an fb, right, we can only produce an f of a tuple b. Like this f is left untouched, right? So we cannot have dependencies such as we have with monad, where we can depend on past values to produce future effects. We can only sequence these operations. So it means that the effects, the final context, the final effects are statically analyzable. And this is a very nice property. We're going to see that in some later in some exercises. And this is a very short example of a fictional DSL, applicative DSL for building, for parsing config files or for parsing configs from the environment. I'm not going to define it, but I just hope that you can see here. This is called applicative notation. I don't hope that you be comfortable with it because I'm going to show in the next slides another nice extension to it. But we're basically, suppose that we have this data type app config. It has these fields we want to get from the environment. And we have these combinators here specifically for DSL, for this env config DSL. And we're basically building this app config thing, which is a function, right, that takes 4 arguments. We're basically building it out of these combinators. This thing here, this string combinator, basically just like tries to extract a string value out of the environment, right? Exactly what happens here after we run it is dependent on the specific interpretation we want, right? But syntactically, I hope that this makes sense to you all. If any of you have any questions here, please ask. But I just wanted to show this slide first, right? Given that same type, like hopefully this here is a little more obvious to you for those who are familiar with do notation. Can everyone like sort of take a guess of what is happening here, understand what is happening here just by taking a look at it? Cool. Yeah, this happens because of like this applicative do extension where Haskell is able to basically like desugar this expression into this here. Like when we don't have any sequential dependencies between the values here and the effects here, right? From the things that are left to the arrows to the things that are right to the arrow, right? So it's able to desugar this into that expression. Another thing we can use are monads, famous ones, and monads are basically just like defined in terms of this operation, this bind operation. Every monad is an applicative functor. It's not like that. In Haskell, you can have a monad that's not dependent on applicative, but let's suppose you need to, just so we don't have to define all the operations here again. But hopefully, you can all see here that given this type signature, with monad, we're able to have sequential dependencies between values and effects, values and context, right? Because given this M thing, which is an applicative and a functor, right? Our effect and our context is encoded inside this M. Given an M of A, then we're able to, given an A, we can produce an M of B, right? So we have a dependency between the values that are produced in this context and the effects that can be produced in this context, right? So we get this nice sequential composition thing. Is everybody able to see that here? Okay, cool. If we now extend that basic app config data type with this email default from, it's a maybe string, right? We can just say that it now depends on whether email key is defined or not. We want to pass this value, right? So we can now see here that email key appears right to the arrow, so sort of right. If we inline this thing, it appears to the right. So we can now have a dependency between values and context here, right? So the important thing here is, though, that this thing is not statically analyzable. Like the effects that are produced here are not statically analyzable because we have dependencies from between values and effects. So anything can happen given what what happens, what values the effects produce. Anything can happen in the effects, and this is a very nice thing to keep in mind, that like a lot of times you want a DSL to be statically analyzable, the effects, because a good use case for me at least is documentation. When you have an applicative DSL, you can add some constructors to it, you can add something to it that makes documentation statically analyzable. So you can produce documentation statically before even running, before even interpreting your values. And I think this is very valuable to a business. And back to the expression problem and the duality between deep and shallow embedding. I'd like to introduce something that attempted to solve the expression problem. It's not a perfect solution, but it helps a little bit, which is tagless final. Some of you may have already heard of it, and it's not hard at all. It's pretty simple. We basically just use type classes as syntax and instance as semantics for DSLs, right? So for those of you who have already used monad transformers and MTL, this is basically what MTL uses, right? When we have the monad reader class, monad state, monad writer, whatever. And you can just like build this huge monad, this huge abstract monad that implements all of these type classes, and then only when you're going to interpret these values, you instantiate it to a concrete value, right? And to go over an example by Oleg Kiselyov, we're going to see a small DSL for building math documents, right? Suppose we have like a monoid D, and we can say then that D is a math doc if it interprets these operations. There are no laws here, but yeah, that's one thing also people complain a little bit about tagless final, which is like we're abusing type classes, lawless type classes to implement these things. I don't see any problem with it because like, I don't care too much about that. But given a tax, we can produce this math doc D. Given this dash is an operation that takes two math docs and produces another math doc. This is like the subscripting operation, superscripting operation with a caret and a fraction with the slash. Hopefully everyone can see that this defines a syntax, right? Sort of, yeah, and Waverly, this describes a syntax because like if we have a math doc, we can compose these operations and build something more complex out of simpler elements. So this sort of describes a part of a language. But now we want to actually implement the semantics. So what we do is basically we define a data type and we define an instance, which is effectively our interpreter. So this can be seen as a sort of shallow embedding, right? Because we're just using the semantic domain there for as our data type to which we're interpreting, right? And so given that we can implement a trivial monoid for this LaTeX data type, we can say that just embedding a text inside it is just using the LaTeX constructor. And now subscripting, we use the underscore thing from LaTeX. Superscripting, we just use caret. And for fractions, we just use frac, backslash frac. And so now, can anyone see how exactly does this solve the expression problem before I jump to the next slide? Like how exactly can we add new constructors to the language, and how exactly can we add new interpreters without having to refactor code?
So adding a new constructor would be adding yet another method of the mathdoc type class. And then we need to go through all the interpreters, instances.
Yeah, but that's an option, but that doesn't solve the expression problem because you still have to touch existing code.
Oh, you mean, yeah, we can also use the type class as a building block and build a larger, if that's enough of a core language for us, then we can define just pure functions that only depend on the mathdoc class. And, I don't know, say a paragraph. Or whatever, yeah.
Yeah, sort of, like that solves a small part of it, but the thing with this technique is that we want both vertical and horizontal extensibility. Like we want extensibility by being able to add new interpreters. This is called vertical extensibility, where we want to suppose we now want to interpret this thing into HTML, right? What we do, hopefully some of you can see that we just add a new instance, right? Because instances are interpreters here in this case, right? We just add instance math.doc HTML. What about horizontal extensibility, like adding new terms? We just add, it's the next slide, but we just add a new type class. We add a new type class, and then we can have more constraints. I'll go over that. But like vertical extensibility first, we just, if we want to interpret this thing into basically just a string for show into the whatever debugging, I don't know. We just add a new instance, right? That's sort of trivial. But adding new operations, we can add new type classes. Suppose we now want to add Greek letters to our documents, right? We just add this new type class Greek here, which has a single method, Greek, taking a Greek letter 2D. This is just implementation details of how exactly we make this thing sort of type safe. And if we want to add like the circle symbol now to our documents language, we just add this new type class here with a single method, which is a circle. Sure?
Is stateless final used for encoding programming languages in general, like lambda calculi?
Yes, exactly. Like Oleg has a ton of papers about using that to embed lambda calculi in Haskell, even the linear lambda calculus.
Oh, wow.
And yeah, I've tried decoding that, but it was pretty dense. So like, and yeah, but the cool thing here now is that we can define documents abstractly. And type inference works for this as well, right? If we want to define this document one as just alpha subscribed by 1 and with a caret on the top, with a circle on the top, right, superscript. This is just an abstract document D, which implements these two type classes, right? And type inference works here pretty well. We don't have to define this type here, this type signature. What if we want to interpret these things into real values? We just add a type signature, like specializing this value, for example, to string. Doc1 string is a string, and it renders to us this beautiful thing here. If we want LaTeX, we just specialize it to LaTeX, and it renders this thing here to us. Cool, right? Everybody following here? Anybody has any questions here? I think the next slide, oh, it's not a questions slide. Okay. So the thing with tagless final is that composing constraints means defining capabilities, right? When you compose multiple constraints that each of them define their own set of constructors, their own set of primitives, their own set of syntax elements to our language, this means that if we compose those constraints, we're defining basically capabilities that this abstract type can have, that this abstract syntax can have. As I've said, MTL uses tagless final for expressing effects, composition of effects. But the thing is that type classes can be problematic sometimes, especially when they get too complex with multi-param type classes, functional dependencies, and type inference can get a little buggy sometimes because of that. But it is nevertheless a very good tool, and it partially solves the expression problem really well. So now we're going to see a real-world example, perhaps could be labeled real-world, but it's a concrete example about a DSL for business rules and validation. And the goals here are basically we have a set of events in our application. Suppose we already have a web application running, and we dispatch a bunch of events in that application. The user accesses our system and registers in the system. They buy a product, they view a product, etc. We want to validate these events given the data that these events produce, they contain. We want to, for example, validate a purchase, validate a registration, etc. And we also want to perform some operations after these events, like sending emails to the user, updating the database, etc. All of this is going to be done abstractly because we don't have too much time, obviously, to update the database, to set up Postgres here, etc. So I'm mostly going to use a pod string line for the effect. So suppose we have this domain, right? We have a data type defining our registration, a data type defining user, billing info, purchase, and product. You can think of these as whatever you want. These are not very important. Just like make sure that these exist. We have an environment, right? For example, whenever an effect is dispatched, we have maybe a user who is authenticated in the system, right? As I've said, validate events in an environment. So what we'd like to have is basically this. We'd like to basically have a set of business rules defined like this, like in order to buy a product, we have to validate purchase, where purchase is a function, validate purchase is a function that takes a purchase and produces something else, right? In order to register, we're going to validate registration. After buying the product, we're going to send a purchase email, okay? Using rebindable syntax, we can write it in this nice way. And like each of these validation rules, like for example, validate purchase, they can be defined as this sort of this thing, right? In order to validate a purchase, given a purchase, we first authenticate the user. Authenticating the user is defined here, right? We get the environment, and we check whether the current user, whether env user exists, where env user is this thing here, right? It's just an accessor function for that record. And after existing that the user is authenticated, we want to check whether the ordered quantity of a purchase is available, whether the ordered quantity of the purchase of the ordered product of the purchase is available, right? Once you match these, and basically just like check whether like the quantity of the product matches is at least greater, can satisfy the ordered quantity. Validate a user billing, we just check whether the billing info of the user is present, and okay. So what is a possible solution for this? Like, it's a lot of stuff going on probably. So how exactly can we start thinking about a solution for this? A good idea is firstly to think about our constraints, right? Enumerate them like this. So first of all, validation rules depend on an environment. We have seen that. It depends on whether the user is currently authenticated or not. Validation rules are sequentially composable. We have seen here that if this whole thing is a validation rule, right? This whole thing is a validation rule. We want to be able to access the user here who was authenticated by this authenticate rule and check whether their billing info exists. Okay. Business rules can be combined. We'd have seen that here, right? Just combining a bunch of business rules. And the input to a validation rule or to an effect after an event must match the event's contents. This can be seen here, right? In order to buy a product, we must first validate the purchase. And this thing takes a purchase. So it must in some way match whatever we put here inside this buy product event. Oops. And dispatching an event to a set of business rules must give us back maybe an effect. That is like the final constraint we must need in order to see this thing in action. We can't see it currently, but we'll be able to see that. So a way of defining our effects, for example, is this, right? A normal data type. So a buy product event contains a purchase, a register event contains a registration, view product contains a product. Okay, so any of you has any ideas of how we can attain any of these constraints? What tools can we use from our tool belt to satisfy these constraints?
Types.
Yeah, types, for sure.
So you kind of revealed some of them already in the examples.
Yeah.
So, and sequentiality immediately brings monads.
Exactly.
And combining suggests monoids.
Exactly.
And also default in the source.
Exactly.
From the meta, I think that you'll have Douglas final in there.
No, actually I don't, just because we don't need extensibility here. So for the first rule, given that validation rules depend on an environment, some of you might be familiar with a reader monad. We're not going to use it here, we're going to use just functions because they're isomorphic to it, right? So if we are given the promise that we're going to have an environment and we want to access it either way, even if we don't have it right now, we can just represent this as a function from an environment to another value, right? So there's a solution to that. Validation rules are sequentially composable. I forgot to actually add a new constraint, which is like, if a validation rule fails, all the other remaining rules must fail, right? The whole thing must fail. And for those of you who are familiar with a monad instance for maybe, that's exactly the behavior we need now, the short circuiting, right? If we combine, we sequence a nothing with a just, we can have anything because we first had the nothing, right? So I think we're going to just going to sit here and do some live coding. Hopefully it all goes right. Can everyone see the screen?
Should I make the text a bit bigger?
Sure. Is that okay?
Yeah.
Okay, cool. Is the whole screen visible there? Not totally. Just gonna drag this thing here. Oops. Okay. So, first of all, we can see that we have two DSLs here, right? One of them here is used to build these business rules. We're making the separation between business rules and validation rules, right? So we basically have two different languages here, and we have two ways, two syntaxes and two semantics in this sense, right? So we have a way of embedding a validation rule inside a business rule, and that can be considered an interpreter. And we have a way of like interpreting business rules into effects, because that's our fifth constraint here, right? Into maybe an effect. So how exactly can we go about implementing this type validation? So first of all, as I've said there, we depend on an environment. So we could just add a function here from an environment to something else, right? And this means that inside every step of the validation computations here, of these validation computations here, inside each and every step, we have access to an environment that's going to be given to us later on. But that isn't, it's important that we have always access, we always be able to access this environment. The next thing we'd like to interpret, to implement is like the short-circuiting behavior. So we use maybe for that, right? The cool thing here is that in order to sequence two of these computations, right? If the next computation depends on this A, which is the result of the previous computation, this maybe needs to be adjusted, right? Because if it is a nothing, right? Maybe A equals nothing, or just A. If it's a nothing, we don't have any A to provide to the next step of the computation. If anybody has any question, please interrupt me at any time. Okay, is everybody following so far? Okay, so now in order to implement this, the second constraint, validation rules are sequentially composable. We need to be able to implement something. Someone has said that we need monads here, right? That's exactly what we need in order to sequence these computations. But first of all, we need to implement some instances, right? All the way up to the monad instance. So we must first implement the functor instance to this data type. I'm just gonna type it here. Hopefully this is okay for everyone. And then we go fmap f2k env. I think this is going to build. This doesn't build. Okay, this builds. Okay. So now we're left with other two instances to build, right? The first one, the applicative one, means that we can sequentially compose these effects, where by effects I'm talking about these two capabilities we have in this validation data type, which is accessing this environment and the short-circuiting behavior given by maybe. And we need to implement these two functions in order to do that. From the signature of apply, we know that given a validation env of a function, we must be able to, and given a validation env of an A, must be able to produce a B, okay? Man, live coding is hard.
Alternatively, we could derive those instances and just test the laws for them, right?
Exactly, we could derive them if we wrote them as in terms of monad transformers, because we could do derive like generalized deriving, derive any class. I mean, we can even derive monad and applicative for those.
I'm not sure. I think applicative, I'm not sure.
You can use deriving via for that.
Yeah, deriving via for sure, yeah. And generalized node type deriving, true. But yeah, I'm not going to do that here. I could have done that for functor. Yeah, that would have been faster indeed. But yeah, so I should have actually added these. It's not too much helpful. I'm just going to jump to the final code here. Validation, okay. Yeah, I'm just going to go to the final code. So suppose we have these instances, right? Functor means that just this thing can be treated as a context. This validation can be treated as a context, and we can map over the value that it contains, right? Applicative means that we can sequence these operations so that we don't have sequential dependencies between value and effects and contexts. The monad instance means that we can have sequential dependencies between values and contexts, like previous values can influence the future contexts we get. So this is our syntax. It is shallow embedded. It is defined in terms of our semantic domain, right? Which is like an environment to a maybe, a value, a valid value, right? We have seen that we have two combinators here, is and exists. These are the only two that appear. This done thing is just syntax sugar. I'm going to show it. And off two, right? So we just have two basic combinators here, is and exists. Hopefully everyone can see that available returns a Boolean here because of the comparison, right? So is must be able to turn a Boolean into a validation rule, right? So just pattern match on it, check if it's true. If it's true, we return just unit. If it's false, we return nothing and short circuit the whole thing, right? Exists takes a maybe a thing and turns into a validation rule. This one is easier, it's sort of obvious. We just do validation const, right? We just do validation, oops, ignore the first, the environment. We don't need it for this rule, and return the maybe a there. Everybody following so far? Any questions? Please interrupt me at any time. Okay, in order to get an environment, we must need only to return it from here, right? This is the basic ask for monad reader, right? And we have some syntax sugar here. Just off is just applying a function, and done is just the returning unit, okay? Okay. So this is sort of the easy part. Like this thing is isomorphic to a very common monad, like just read the T maybe, okay? So the more interesting part happens here when we try to build this whole thing here, because of these two constraints here, these three constraints here. Like the third one is pretty simple, but this one here is the most interesting one, right? How exactly do we match the input to a validation rule, or to an effect, for that matter, to the event that was dispatched? If we see the events definition here, which is somewhere, okay, here, right? We can see that an event in our case, for example, is a data type that has a bunch of cases in it where each of those contains something, okay? So, oops, was not to be seen. So how exactly do we go about matching these two things here? How exactly do we go about matching the purchase that's contained inside the byproduct event with the purchase that is needed by this thing here? Anybody has any ideas? And it's important that we see here that all of these events, they have different contents, right? So we cannot parameterize the whole business rule type by an event, by the contents of an event, right? Because we must be able to combine different event types here. Does anybody have any idea?
Use a generalized algebraic data type, I guess, approach, right?
Yes.
So,
But exactly why do we need a JDT?
well, because the types, as you said, are different of each constructors.
Exactly.
Constructors, but still they have the same form.
Mm-hmm.
So we need to be, on one hand, we need to be constrained to this subtypes, so to say, of this branches of this type, and on the other hand, we need to be polymorphic. So
Exactly. So we need the existential types capability of JDTs more specifically. We don't need exactly JDTs. We could do that with just existential data types, but I'm going to show the JDTs anyway because I've implemented them that way. So exactly, yeah. The gist of the thing here is that in order to match the contents of these events to these validation rules, and at the same time, in order to be able to combine things that take different types here, we need some way of hiding this type here, right? Because this thing is parametric inside this to rule here, right? Because the same E, for example, that is produced here must be consumed here, right? At the same time, must be able to combine different E's here and here and here and here. So we must have a way of hiding this type from the resulting expression. And that's exactly what existential types are for. Just quickly going to show these two things here. Okay, so Right. Focusing on these two things here, right? We have this to combinator here first, okay? It takes this match thing, ignore it for a moment, think that this is just an event, E here, right? Can everybody understand this type, sort of? Like taking an event that produces an A, this is a hypothetical type signature anyway, taking an event that produces an AE, oops, and the validation rule that given an E produces a validation monad, we must be able to produce rules of this event type, taking this environment and producing this M, which is like the effects that we can produce from those rules. Can everybody see sort of what's going on this type signature here?
So we are hiding the results type of each validation when we embed them in the rules, right?
Yeah, this could be just unit for that matter. That's not important. So yeah, we're hiding something, but we're hiding this E thing here, right? It doesn't appear here by the end. So it is existential in this sense, right? It exists here, but it's not present here, okay? And yeah, the same thing goes for, I'm going to leave it like this. Okay, the same thing goes for the after rules, right? After buying a product, we must be able to send a purchase email. And the send purchase email, I should have added it here, also takes a purchase as an argument, okay? It takes a purchase as an argument, it produces an effect as a result. So after an event that produces an AE, given an environment and that E, we must be able to produce an M of A, right? And that gives us back a business rule, which is the same business rule that's produced by a 2. So we can combine these two, as a matter of fact, okay? How exactly do we go about encoding those as proper data, as proper syntax? We must need a way of hiding this thing here, right? I could have went with shallow embedding, but I wanted to show a deep embedding because we get the chance to see GADTs or existential data types. So these are rules that can be combined, right? As a monoid here, okay? But in order to represent each of those individual rules, like here I've defined rules to be just a list of individual rules, okay? We must be able to hide this E thing here in the types, and that's exactly what GADTs and existential data types are for, okay? So a single rule, as we have it here, it can be just like a to or an after. I've chose God to represent to. I could have just added to here, but it made more sense to me to call it God. So yeah, I should have talked about this thing first. Okay, so in order to, like, from any of these events, in order from any event, we want to be able to produce a purchase, a registration, and a product. How do you go about doing that polymorphically? We could have added like a type parameter here, E, right, in order to represent like the types and use GADTs for that, but we're not doing that. We're using just a basic function, right? So if we're given an event, we can produce maybe a purchase, maybe a registration, and maybe a product, okay? Hopefully everyone can see that because we can just...
It's not always valid, right?
Exactly, it's always valid, and we can always just pattern match on this, right? In order to, okay? Just going to rewrite this like this, okay? In order to buy a product B, right? If we're given an event of type by product, we can produce a purchase. If we're given an event of type by of any other type, we cannot produce a purchase. Okay? And this thing here, this type of function here, is called a prism. I've called it match here just because it matches an A, right? It matches an A in this type F. Okay, and extracts one from those. The bell is almost ringing. So, yeah, I think this is a good place to end it, and we're going to start from here in the next session.